Hi everyone. In the previous lecture, we introduced the idea of operational amplifiers. We said that an operational amplifier is an ideal operational amplifier is a hypothetical three-terminal device with an infinite gain. The output voltage will be an amplified version of the difference between the voltage at the input nodes. We said this was a mathematical block diagram representation for it. And before we analyze, I'll just, for the sake of formality, I'll just introduce a few very commonly used Opamp circuits. And then we will talk in more detail about them in the upcoming lectures. So shown here is a classic negative feedback amplifier structure. So you have an amplifier in the forward path. So this thing, we said this structure, which is the difference plus an amplifier together, we called it as an operational amplifier. When it is configured in a negative feedback mode, the error signal E here is given by 1 by 1 plus A beta times X. If A beta is infinity, if A beta tends to infinity, then the error will tend to 0, which means the plus terminal and the minus terminal voltages will become equal. Now this is a very important point to understand, because throughout the analysis of operational amplifiers, mainly they are used in negative feedback circuits. In a negative feedback mode, and in all those modes, all you need to do is just to equate. If you know that the circuit has a negative feedback, then all you need to do to analyze this Opamp circuit is just to equate the positive and negative voltages. You should just equate the two voltages, or the difference between the two voltages will be 0. The two popularly used Opamp configurations or the inverting configuration shown here, where the input signal is applied at the inverting or the negative terminal of the Opamp, and the other configuration here, it's called the non-inverting configuration, where the input signal is applied at the non-inverting or the positive terminal of the Opamp, positive input terminal of the Opamp. Now mind you, in both these amplifier topologies, the feedback is negative. It's only the difference is where you are going to apply the input. So in this circuit, if you see, there is, for example, if you see the circuit, we have already discussed in the previous course on microelectronic circuits how to break a loop and find the loop gain. We can do that for both these circuits. The loop gain will be same for both the circuits, and we can also instantly see that both these circuits have negative feedback. If I break the loop at this point, and if I traverse and return to the same point, we can immediately see that the loop gain will be negative, so which means it's a negative feedback. I can apply the similar procedure here. I can break it here and return to this point. Instantly you will see that the gain will be, in fact you can easily write the loop gain will be minus of A into Zi by Zi plus Zf. So this is going to be negative. So right now I'll assume the impedances here are pure resistors. Then it's going to be negative, and the feedback will be a negative feedback. Now, if the feedback is negative, we just saw that the error signal will go to 0 if the loop gain A beta is infinity. Now, if A is infinity, and I'm going to assume for the time being the impedance ratio is also finite, then this term loop gain will blow up to infinity. If the loop gain blows up to infinity, A beta blows up to infinity, the error goes to 0, which means the voltage at the plus terminal and the voltage at the minus terminal will become equal. So if you use this, the analysis of operational amplifier circuits is quite trivial. So now first I'll quickly use that and show you what will be the voltage gain for the circuit, and then we will draw the conventional block diagram approach of solving an Opamp circuit. So since I said that there is negative feedback, so this node voltage is at 0, so this node voltage can also be assumed to be at 0. Now since this node voltage is 0, the current flowing through this impedance Zi, the voltage across Zi is Vi, so a current of Vi by Zi is developed in this impedance Zi. Now that current has only one path to flow through. It will directly flow through Zf, and since we know one end of Zf is the output voltage, the other end is at 0 volts, and the current direction is in this way, So you will have a voltage of Vi into Zf by Zi develop across this impedance Zf. The entire current flowing through Zi has to flow through Zf. So the voltage across Zf is given by Vi by Zi into Zf. But since we are taking the voltage at this node here, so there will be a negative sign. It will be minus of Vi into Zf by Zi. Now, one thing is quite intuitive to see here is that there is no other path for this current, so the entire current has to flow through this impedance Zf itself. Okay, so that's something that's quite obvious because the input impedance of the op-amp is infinity, so no current can flow through that. Now, you can also look at it in a different way. An operational amplifier, for example, in fact, we will talk about this more at a later stage. An operational amplifier with feedback, some impedance in feedback, if I inject some current, the entire current will be fully absorbed by this op-amp. So the only path for it is it has to flow through this impedance Zf. We can directly see by the application of Miller's theorem, the input impedance is Zf by 1 plus A. So if A is infinity, the input impedance is 0. And the output voltage here is proportional to, in fact, is equal to minus of I times, depends on the direction of current. If I assume the direction is in this direction, it's minus of I into Zf. So it looks like a trans impedance amplifier. I mean the impedance Zf and the op-amp together behaves like a trans impedance amplifier. So the input impedance is very low, which is Zf by 1 plus A. And the output impedance, of course, it's the output impedance of an ideal voltage amplifier, so that's also very low. So it behaves like a trans impedance amplifier, current input, voltage output. So you can look at it that way as well. But even without this, even without looking at it this way, you can solve the circuit. Now, one thing which we will discuss in more detail in the next lecture is a very important thing to note here is that, so this configuration, it's called as an inverting amplifier configuration. The voltage gain, since we saw V0 is minus of Vi into Zf by Zi, so the voltage gain will be minus of Zf by Zi. I can replace this impedance Zf with capacitor, inductors or resistors and get different frequency response transfer functions of different frequency response. So since there is a negative sign here, we call it as an inverting amplifier. Similarly, the amplifier shown here, since this is a negative feedback and the loop gain is written here, and since for an ideal op-amp A is infinity, so loop gain is infinity. The moment we say loop gain is infinity, the error has to be 0, which means the error is nothing but the difference between the voltage at this node minus the voltage at the negative node has to be 0, which means both the voltages will be same. So this node voltage comes to Vi. So if this node is Vi, the current flowing through this impedance is Vi by Zi, and that current has two paths. It will only, because the input impedance again is infinity for the ideal op-amp, it has to fully flow through Zf, and the voltage developed across Zf will be Vi into Zf by Zi. And the output voltage, the voltage at this node, will be the sum of voltage across this impedance Zf plus the voltage across this impedance Zi. So that will simply be Vi into Zf plus Zi plus Vi. So you get a transfer function of 1 plus Zf by Zi. So this here, it's called a non-inverting amplifier. There is also a block diagram way of analyzing this circuit or looking at this, interpreting the circuit. First, I'll start with a non-inverting amplifier. It's very simple to analyze it using a block diagram approach. I'll just replace this op-amp by this summer and an op-amp, an amplifier with a gain A. And the fedback quantity here, so there is no current flowing through the input of the op-amp, so the fedback quantity is simply Zi by Zf plus Zi, so that's your beta here. So that's beta here, and this circuit here can be directly represented by a very simple mathematical model, the conventional a simple negative feedback control loop model. Now we already know if A is infinity, if the forward path gain A is infinity, the loop gain is given by 1 by beta of S. So it will simply be the inverse of this. So it's going to be 1 upon this, so which will be 1 plus ZF by ZI. On the other hand, if I consider a non-inverting amplifier, the block diagram will not be as simple as what we drew for a non-inverting. We have to see that the input signal, the signal at the inverting terminal, it's affected by two node voltages. It's affected by the node voltage Vi and the output node voltage V0. So I can use principle of superposition to calculate what will be, let Vx be this node voltage. I'll calculate this node voltage Vx as a fraction of Vi, so Vi times, so I'm using principle of superposition, so I'll make V0 0 and it will simply be a potential division between Zi and Zf. So Zf here and Zi here, so you get Zf by Zf plus Zi. And similarly, I'll ground Vi and calculate the contribution due to V0, you get V0 into Zi by Zi plus Zf. Now this is the input which is applied at the negative terminal of the op-amp. So to show this circuit, I've drawn the block diagram in a block diagram format. I've shown it here. So one terminal, the positive terminal of the op-amp is at 0, which is at ground. The negative terminal is the sum of two quantities, which is Vi times some fraction and V0 times some other fraction. So this is V0 times here, this is a feedback quantity, so I'm going to call this as beta of S. So voltage is fed back and a fraction of it is added it with the input signal. Both these signals are then fed to the negative terminal here. Again, the same logic holds. Again, I can just do some quick modification of the diagram. So I can just remove the summer and bring the minus sign at both these terminals. So I'll bring the minus sign here into this gain factor, which is the fraction Zf by Zf plus Zi, and I'll bring the other minus sign to this node, to the summer term. I can just make it a negative. I can either bring this minus sign into this fraction as well, but I can simply, because we are more familiar with this negative feedback control loop model, so I've just brought this negative sign here. So this is the reduced block diagram representation of an inverting amplifier. We know this part can be immediately reduced. We can recognize it's a negative feedback amplifier. 1 by beta of S will be the transfer function, so it will be Zf plus Zi upon Zi multiplied with the input transfer function, which will be minus of Zf by Zf plus Zi. So you will directly get minus of Zf plus Zi. So it's a little bit slightly more complicated way of looking at it, but this is a simpler or a block diagram representation of an inverting amplifier configuration. So using this, we'll quickly see some circuits, but a point that I want you to remember, which we will talk in greater depth in the next lecture, is that this node, the voltage at this node is at ground. So, I mean, it can be an AC ground or a DC ground. Then this node Vx, if there is negative feedback in the circuit, we just saw error has to be 0, which means Vx has to track the positive terminal. So that will also be at ground. So to distinguish Vx from the actual, so here this is an actual ground. To distinguish it from that, we call it as virtual ground. We'll talk more about that in the next lecture. But right now, I just want to put that thought out there that this terminal, we are going to call it as the virtual ground. And it's especially the case in an inverting configuration. Now we'll quickly see some topologies, because we discussed in the previous lecture that using op-amps we can build integrators, differentiators, and some simple voltage gain elements, or even adders and subtractors. So shown here, the impedance, the feedback impedance is replaced by a capacitor. So we can directly write minus of Zf by Zi, so the transfer function for this, so which is minus of 1 by Sc into 1 by R. So it will be minus of 1 by SRC. The transfer function is that of an integrator. So since there is a negative sign here, it will be called as an inverting integrator. But what is actually happening here is that if you look at how to build an integrator, we know that the voltage across a capacitor is nothing but the integral of current flowing through it, or current flowing through the capacitor is derivative of the voltage across it. Now if I can somehow generate a current which is proportional to the input voltage, then and then I take this current and push it into a capacitor, then the voltage developed across the capacitor will be the integral of current through it. And since current is proportional to an input voltage, the voltage across the capacitor will be proportional to an input voltage. So that's what we are doing here. So we said this node comes to virtual ground. So the current flowing through this resistor is VI by R. So I am using a resistor here and generating a current which is proportional to input voltage. So that can be done using a resistor. And then that current will fully flow through this capacitor, and therefore the voltage developed across the capacitor is going to be an integral of this into 1 by say integral of voltage dt. So that will be the voltage across the capacitor. And since we are measuring the voltage at the output terminal, you will get a negative sign here. The reason why I am saying you get negative is that if you see here, this node is at AC ground, okay, or rather in this circuit probably it's at ground itself, and the voltage here it's positive, meaning this voltage is supposedly higher than this potential, or this potential here is supposedly higher than this potential because of the direction of flow of current. So therefore your output voltage will be lower than ground. So that's why the negative sign here. So in the same way, if I want to build a differentiator, I can just replace this capacitor with an inductor. If I replace the capacitor with an inductor, we know the voltage across an inductor is nothing but the derivative of L into di by dt. So it's nothing but its derivative of the current flowing through that. So if I generate a current proportional to the input voltage, then the voltage across the inductor will be a derivative of the input voltage, proportional to the derivative of the input voltage. But generally, we don't use inductors. We try to avoid where possible. Generally, they are bulky, so we try to avoid them. So using capacitor itself, if you can build a differentiator, it will be much simpler. So that's what is shown in the second circuit here. We can directly write the transfer function by using the well-known result, which is the feedback impedance R with a minus sign divided by the input impedance, which is 1 by SC. So you'll get a transfer function of minus SRC. So you can see it's already a differentiator. Or we can see it this way. Instead of generating a current which is proportional to input, if I can generate a current which is a derivative of the input voltage. So that's what is done here. So since this input voltage appears entirely across the capacitor, the current flowing through the capacitor is a derivative of the input voltage. And if I push this current into a resistor R, so I said that this Opamp with a resistor here behaves like a trans impedance amplifier. So if I push that current, the output voltage, if I push that current to the resistor, the output voltage will then be proportional to, it'll actually be minus of I times R, and I is nothing but C dVA by dt. So you will get RC or CR into dVA by dt. So you have a differentiator there. So these circuits cannot be built as it is. So we'll have to do some modifications. I'll talk about that at a later stage. But what we have shown here is very simple, in very simple way, how to realize an integrator and a differentiator. Now shown here are two voltage gain circuits with built using purely resistors. So this circuit here, it's a non-inverting amplifier. The gain is given by 1 plus R2 by R1. I mean, it's just the beta is R1 by R1 plus R2. You take one upon that, you get the gain for it. Now this circuit here is a non-inverting amplifier. Again, you can look at it in a similar way. All I need to do, if I want to get a gain out of an amplifier, I'll first generate a current which is proportional to input, and then push it into a resistor, another resistor, then such that the product of this current into resistor should be greater than the input voltage applied. So that's why I'm going to choose the resistor values. If I do that, then I have amplification. So that's what, in very simple terms, we are trying to accomplish that using these circuits. So this is an inverting amplifier, and this here is a non-inverting amplifier. I'm just introducing the terms here. That's it. We will talk in greater detail about these amplifiers at a much later stage. There are other realizations of integrators and differentiators. So for example, if we saw here, the voltage gain was realized in both non-inverting and inverting configurations. But when I spoke about differentiators and integrators, we spoke only about inverting configurations. So how does one realize a non-inverting integrator using just one op-amp? Now of course, we can cascade this inverting integrator with a gain of -1. With a gain of -1 built using a circuit like this, then I can just get away with the inversion sign. So multiplied with -1, you get a positive integration. So you get a non-inverting integrator. But we can actually do that even without using an additional op-amp. So first, shown here is the circuit. The operation principle is very similar. First, generate a current. So the conceptually, you can look at it in many ways, but since we discussed this intuitive way where we said generate a current and push it into a capacitor, generate a current which is proportional to the input voltage, and then push it into a capacitor, you have integration. So now that's what we are doing here. So in a non-inverting configuration, we said, of course, when there is negative feedback, the negative voltage will be VI. So we are generating a current. If you put a resistor from the inverting terminal to ground, the current flowing through the resistor will be VI by R. Now push this current into a capacitor. So the voltage across the capacitor then is going to be integral of VI by R into 1 by C dt. So we have an integral there. So the voltage across the capacitor here will be an integration of the input voltage. But here we are actually measuring the voltage at the output terminal. So here we are measuring the voltage at the output terminal, which is nothing but the sum of the voltage. I'll probably redraw the capacitor. So which is nothing but the voltage across the capacitor plus the voltage across the resistor. So the voltage across the capacitor is actually 1 by RC integral VI dt plus the voltage across the resistor is VI. So we are getting an additional term which is proportional to the input, and if you want to eliminate this, you can subtract VI out of it, and that subtraction can be performed using an additional op-amp. But can we do that without using an additional op-amp? If I want to get rid of this term, if I want to have an integration, a pure integrator 1 by SRC using just a single op-amp, that can be done by looking at the transfer function, by making some small modification to the circuit, keeping the transfer function in mind. So first, the transfer function of this circuit, we said the voltage across the capacitor, I'll write it in Laplacian domain. You have a current VI by R flowing through an impedance 1 by SC plus VI equals V naught. So the transfer function is 1 plus 1 by SRC. So which can also be written as 1 plus SRC upon SRC. Now I need to get rid of the numerator term, which is a 0, 1 plus SRC. Now to get rid of this, I just need to multiply it with the term 1 by 1 plus SRC. Now this 1 by 1 plus SRC, it's nothing but a simple low pass filter that can be realized using a passive circuit itself. A passive RC circuit will directly give me the transfer function 1 by 1 plus SRC. So that's it. We take an non-inverting integrator circuit, cascade it with a passive low pass filter, RC low pass filter, you get an non-inverting integrator. So mind you, here we haven't really worried about the practical considerations about implementing this op-amp. So when we implement this op-amp, we'll have to worry about many other constraints like common mode and all of that. But right now, we're just playing with a simple hypothetical 3-terminal element, using this how to build different circuits. We are just playing with that idea, toying with that idea. In a similar way, we'll try to realize a differentiator as well. So the same way, generate a current which is derivative of the input voltage and then push that current into a resistor. So that's what we are doing here. So using a non-inverting amplifier, the positive, I'm applying input at the positive terminal. So this will also be equal to Vi, which is appearing entirely across a capacitor. So the current flowing through that will be C dVi by dt. Push it into a resistor. So multiply with R, that will be the voltage across the resistor. So the output voltage is the sum of voltage across resistor plus the voltage across the capacitor. So again you have an additional term Vi. So the desired transfer function is SRC. But what I am getting here is if I take the Laplace transform of this term, you are getting 1 plus SRC. So I need to get rid of this term 1. Now one thing we can look at it is if I want a transfer function SRC starting from 1 plus SRC, if I can multiply this with SRC by 1 plus SRC, a simple high pass filter realized using a passive RC circuit, then the product of these two will give me an ideal differentiation. And this transfer function of SRC by 1 plus SRC can be readily realized using a high pass RC, first order high pass RC filter. So here what we have gotten here is a non-integrating differentiator using just one op-amp and passive components. Now in the same way, one can look at realizing adders and subtractors using this very simple idea. So we said that all I need to do is if I want to realize adders, I have to just add the currents, convert the voltages into currents and just add the currents and push all that added current into a single resistor, you have voltage addition. So that's what I've shown here. So this is shown here as a non-inverting amplifier. In a non-inverting amplifier, we know that this node will come to AC ground. So the currents through the individual resistors R1, R2, R3 is given by V1 by R1, V2 by R2 and so on. And then using a negative feedback op-amp, if I can push all this current through RF, so the voltage developed will be proportional to some weighted addition of the input voltages V1, V2, V3 till Vn. So here it's a very simple an inverting voltage adder. Now to realize a subtractor, also probably showing, I'm just showing another circuit here which is a non-inverting voltage adder. Okay, so that can also be built. So this is this circuit is built on a very simple principle. If let's say I take two resistors R and apply voltages V1 and V2 here, the voltage at the center is going to be V1 plus V2 by 2. Similarly, that can be very easily proven using superposition. If you take three resistors, if you connect three resistors at the node and apply node voltages V1 plus V2 plus V3, you will get the voltage at this node will be the average of the three voltages. So you will get V1 plus V2 plus V3 by 3. So what I've done here is I've connected n voltages and resistors. So the voltage at this node is going to be V1 plus V2 plus so on plus Vn by n. It's an average of the n voltages. All I need to do is get rid of this factor n. So I've designed a non-inverting amplifier with a gain of 1 plus R2 by R1. So in this case it's going to be 1 plus n minus 1 R by R. So it will be 1 plus n minus 1, which is n. So what you get at the output is sum of n voltages. Finally, it's a subtractor. If I want to subtract two voltages, of course, the moment using a single op-amp, if you want to generate, you can actually take this adder circuit and probably just invert the polarity of the voltages of your choice. If you want to invert V2, V3, then you get subtraction. And that inversion of polarity can be accomplished using another op-amp. Using a single op-amp, I have shown, this is also a well-known circuit. These are all, again, as I said, it's just a lecture just to review all the op-amp circuits, so that at a later stage we'll talk in greater depth about these circuits. So it's a simple voltage subtractor circuit where you subtract the two voltages using a single op-amp circuit, single operational amplifier. So of course, using a single operational amplifier, if I want to subtract the two, then we know that if you apply an input voltage at the inverting terminal, then the output voltage will be some minus times that input voltage. It will be a phase inverted version of the input voltage. If you apply another voltage V2 at the non-inverting terminal, then the output is going to be proportional to V2. The sign will not get changed. So using that, exploiting that, we can build a simple subtractor. So to do that, to show it how it behaves as a subtractor, you can apply the principle of superposition. If V2 is 0, anyways this node will also come to ground. If this node is ground, the output voltage will be minus V1. Now, if you assume V2 is present and V1 is 0, this node voltage here is V2 by 2, and this circuit here, this behaves as a non-inverting integrator with a gain of 1 plus R2 by R1, which is 2 in this case. So you get plus V2. So the total voltage will be V2 minus V1. So what we have here is a subtractor. So that's it. This lecture I just discussed very briefly about the different possible circuits that one can realize using an operational amplifier, starting from integrators, differentiators, then inverting and non-inverting differentiators and integrators, inverting and non-inverting amplifiers, and finally we also saw adders and subtractors. I'll just end the lecture by just reminding you one thing which we were discussing, is that especially in an inverting amplifier, we were talking about the idea of virtual ground. We said that this node, the inverting terminal here, comes to the same voltage as the positive terminal. In this case it's ground, so this is also ground. To distinguish that, we called it as the virtual ground. The next lecture I'll revise this again and talk more in greater depth about the virtual ground.